Meet Carol, a routing node on the Lightning Network. A payment passes through her. From where she sits, it's a simple transfer. Bob sends to Carol, Carol forwards to Diana. Carol just helped move money between two strangers, and she'll never know who they actually were. That's not a bug, that's the entire point. Now pull back. This was never a Bob to Diana payment. Alice is paying Eric across 5 nodes. Bob is just a relay. Diana forwards onward. Carol has no idea. Every intermediary sees only its immediate previous and the next hop. This makes surveillance, censorship, and blacklisting extremely difficult. To understand how Carol can stay this blind, we need to back up to how a payment finds its way at all. Start with identity. Every node has a long-term public key. That key is its identity on the network, the address other nodes use to find it and encrypt messages to it. All communication between nodes is encrypted point to point. So when Alice talks to Bob, no eavesdropper between them can read what passes. Public key identity plus point-to-point encryption gives us the building blocks. Next, Alice needs a root. Before paying, Alice must find a path of channels with enough capacity. Channel capacity is the amount of Bitcoin locked in a channel and available to move. Nodes advertise their channels, capacities, and fees through peer-to-peer flooding, gossiped across the network the same way Bitcoin spreads transactions. From this map, Alice picks a route. Bob, Carol, Diana, then Eric, each link holding enough to carry her payment. Alice now has her path. Now the hard part, using it without spilling the secret. Here's the tension. Alice must coordinate a payment across 4 hops, telling each node exactly where to send next, while keeping every one of them blind to the full route. Bob can learn Eric is the destination. Carol can learn Alice is the source. The sender must orchestrate the whole journey, while every participant sees only one step. The solution is Sphinx onion routing. Alice builds the onion backward, from the destination inward. First, she writes the innermost message for Eric and encrypts it with Eric's public key. Only Eric can open it. Then she wraps that bundle in a layer for Diana, encrypted with Diana's key, and inside it names Eric as the next hop. She wraps that for Carol, naming Diana. Finally, she wraps everything for Bob, naming Carol. The result is nested encryption, like layers of an onion. Each layer can only be opened by one specific node and only reveals where to send the rest. Now watch it peel forward. Alice hands the whole onion to Bob. Bob decrypts the outer layer, the only one he can open. Inside, he finds instructions to forward to Carol and a sealed bundle he cannot read. He passes it on. Carol opens her layer, sees Diana as next, forwards the rest. Diana opens hers, sees Eric, forwards again. Eric opens the core and finds the payment is for him. Every participant knows exactly 1 hop back and 1 hop forward, and nothing more. No single node ever sees the whole route. What does each layer actually carry? Instructions to extend an HTLC, a hash timelock contract. That's an enforceable conditional payment, payout only if the recipient reveals a secret before a deadline. Each layer specifies the amount to forward, the fee that hop keeps, and a CLTV timelock, an expiration measured in blocks. As the onion moves forward, every node commits an HTLC to the next, hop by hop. When Eric reveals the secret, each contract settles back down the chain. The whole route locks and unlocks like a chain of dominoes. An obvious worry, doesn't the package shrink at each hop, revealing how many hops remain? It does not. Every packet is padded with random data to a fixed size. When a node strips its layer, fresh, random padding fills the gap, so the onion that leaves is exactly as long as the one that arrived. Every node sees the same thing, a next hop plus a fixed length blob. Nobody can count the hops behind or ahead. Only the final recipient discovers there's no next hop. that the journey ends with them. This sounds like Tor, but there's a crucial difference. Tor has exit nodes, the point where traffic leaves for the open internet, and those exit nodes can be monitored. Lightning has no exit nodes. There's no edge where the payment surfaces into the open, and payments never touch the blockchain for routine transfers. Nodes simply update their channel balances. Both use onion routing, but Lightning's version, Sphinx, leaves no public ledger footprint and offers no single point to watch. This single privacy trick reshapes the whole network. Lightning is a second-layer routing technology, running atop any blockchain that supports multisig, timelocks, and simple contracts. Layered on Bitcoin, the privacy architecture cascades. Harder surveillance means fungibility. Every Bitcoin stays equal to every other, non-tainted by its history. The off-chain design delivers speed, millisecond settlements since HTLCs clear without waiting for a block. Granularity, payments at least as small as Bitcoin's dust limit, the smallest amount worth spending, and potentially smaller. Capacity orders of magnitude beyond on-chain, limited only by each node's own capacity and speed. And through all of it, the network stays trustless. Trustless means peers never need to trust one another. Carol doesn't trust Bob, she doesn't even know him. Settlement is enforced by Bitcoin transactions and timelocks, not by goodwill. If anyone misbehaves, the mass and the blockchain protect the honest party. So Lightning doesn't sacrifice Bitcoin's founding principle for speed. It preserves it. The sender alone holds the road. The nested onion keeps every hop blind. Fixed size padding hides the path's length. No exit nodes, no ledger footprint. Lightning keeps everything that made Bitcoin trustless and transforms what it can do, stretching it far beyond simple payments into a foundation for entirely new tools.